Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to explain a new paper called Spelling Correction Model for End-to-End Speech Recognition by Jinxi Guo, Tara Sainath and J. Weiss. This paper is from collaboration between UCLA and Google. And in this tutorial, this paper was released like few days back in archive, and this paper is not yet published in any conference. And the overview of the tutorial is like this. So first we cover the introduction of the paper, then we will see what is LAS model, listen, attend and spell model, which is used in this paper. Then we will see how we can utilize the text data for leveraging or how we can leverage the text data for improving the accuracy of this LAS model. And then we'll see some experiments, and finally we'll see some results. So in the overview, basically, so we'll see why this model was introduced. So basically this in any text to speech or any speech recognition model, we will not take into this character error distribution into account whenever we build any model. So it's a sort of like how the model is behaving basically. And in this paper they show like how they are taking care of this one, and we will understand that in the coming slides. Then also they have built a spelling correction model using only text data, and those are going to be like sort of helping you in improving the accuracy explicitly for correcting the errors which are made by the actual speech recognition. So basically the spelling correction model is like you predict some output, you predict something for a given audio from any speech recognition engine, then we'll use another model which will correct it. So basically it corrects the spellings and stuff. So we'll see that. So that's the second point, as you can see here. And then we'll see the experiments are conducted on LibreSpeech dataset, a very well known dataset, and they show that some improvement on some 18.6% relative improvement over in WER over the baseline model, and also they get around 29.0 relative improvement when they further rescore the model, rescore the outputs with the external language model, as you can see here, right? So, coming to listen, attend and spell model. So LAS. So LAS stands for listen, attend, and spell model. So basically, you have a listening module, which is this. So basically, you take the audio and get the spectrogram of it, or get MFCC vectors of this audio signal. Like for example, if your audio is like this, you first convert this into frames by using by computing MFCC over let's say MFCC for let's say every 30 millisecond or 25 millisecond, and then those vectors are going to look like this. Then you feed it to any module which is going to be like any deep learning module where you have, let's say CNN or RNN, and then the output goes to something called this attention model, where we call this attend. So this is the attend block. So this attention model is going to give some output, and the output from attention goes to the decoder, which they call it a spell model. So basically spell is sort of generating the words or generating subwords, or sometimes generating characters, right? So this is also one LSTM, and this is another LSTM, or it could be like combination of CNN plus LSTM, right? So this is the idea of LAS. Let's say LAS is like you have a listening module where you process your input audio using LSTM. Then you create an attention block. Then the output of attention block goes to a decoder, which we call that spell model, right? So this is the whole idea of listen, attend, and spell, right? Now, given this, for example, in here, as I said, the outputs could be like words, or it could be words is not a good idea to use, because you will have millions of words in any language, and it's basically difficult to create a softmax. So for, like creating a softmax which will give distribution over all the possible, like for example n could be 1 million words, or 1 million words in your English vocabulary, right? So it's a very difficult to create that sort of vocabulary or that sort of softmax. So instead, people go with something called subwords, right? So subwords, or you can actually go with characters also, right? So characters also one idea. So the subwords are going to be the outputs from the spell model. And so the main intention of this paper is how do we leverage any unpaired text. So unpaired text is basically, for any speech recognition you need audio and its corresponding transcript, right? So audio text pair you need for training any speech recognition model. But since we have access to a lot of text data in the world, like for example common crawl has huge amount of text data, so how do we leverage that text data? So one way is to use that data to create a language model, and you can use that language model to and fuse the scores from this language model to the acoustic scores, acoustic model AM, and then you get a better hypothesis. This is a very well known thing. If you see any equation of automatic speech recognition equation, so probability of hypothesis given, let's say, the input x, you also know that you get a probability of x given y into probability of, let's say, y. So this probability of y is basically the probability of the hypothesis, right? And this is a language model, and this is the acoustic model, right? This is AM. So people have already used a lot of fusing techniques where you create the acoustic model and you can fuse the scores from acoustic model with language model to get the better hypothesis. And this is done in many ways. There is something called shallow fusion, where you train your acoustic model separately and language model separately and fuse the scores from these two during beam search, right? Or there is something called deep fusion, and the deep fusion is sort of like you fuse the scores during the training of acoustic, you jointly train both of them together. And there is something called cold fusion also, right? There is shallow fusion. So the shallow fusion is there, and there is something called deep fusion. Then there is something called cold fusion. So these are different techniques where you can fuse the language model, which is trained using only text data with large amount of text data, and you fuse it with acoustic model so that you get a better performance. This is sort of leveraging the lot of available text data to create language model, so that it's going to be helpful in creating a better hypothesis for a given audio, right? The second idea is to use synthesized audio. So the problem with synthesized audio is there's no problem, but the thing is when you generate any at least before 2015 or 2014, the audio which you generate using text to speech engines were not that natural. So basically they had some let's say problems when with the audio, like sounds like external sounds. It's sort of like the audio quality. If you look at the audio quality was not that great. So it was so that was a problem which was causing. So it is sort of like not good for using this text to speech data or text to speech audio generated audio to use it in a ASR, right? And recently NVIDIA guys showed that if you use let's say only TTS data for training any ASR model, it's going to be very bad. The accuracy is going to be very bad. WRS was around 80%, which is very bad. But if you use 50% of the clean or the natural data and 50% of the generated data or synthesis data, then the accuracy was not that suffering. But the ideal thing is you use 30% of the synthesized data with 50% of your 70% of the clean data. Then the accuracy was little bit better compared to the only clean audio. So that was a good idea. That was a good study which NVIDIA people did, and that is also one way where you can leverage your text only data and create synthetic data using that text, using any text to speech engine. And these days there are very good text to speech engines which can generate very natural audio. For example, parallel wavenet. There is a parallel wavenet or normal wavenet, you can call. There is parallel wavenet, is very well known and it's good. It's a very fast synthesis engine also. Then there is this Stacotron, and then there is this deep voice. Uh, yeah. So that there is a deep voice. Then there are many actually. There are car to wave. So there are many text to speech engines which you can use, and parallel wavenet has shown that they get very good mass score. They get very good mass score. Plus the synthesis time, that it's also a real time. It's faster than real time actually. Right, that's a one way. And third one is using synthetic data. Sorry, spelling correction model, where you create a model which basically maps your output from let's say the LAS model or any speech recognition model to the correct transcript, right? So whatever output we get from LAS model may not be that accurate. It may have mistakes in spellings and stuff like that, and you map that to correct transcript. During training, if you do that, and testing, you can easily take the LAS output and feed it to the model. It will predict the correct output. Right, that's another way of doing. Other way of leveraging the text only data for creating a better speech recognition model. So in this paper they have used all three of them. So basically they show like using all three you get a little better performance. So we'll go through one by one. So first thing is if you use let's say external LM. So external LM is basically you can fuse the external LM in different way. I mean there are different ways of creating external LMs. Like for example there is a n-gram based language model, and there is RNN based language model. You can create any LM you want, and here they have created RNN LM. So from the RNN LM you can compute the joint probability, or you can compute the probability of the hypothesis Y using the LSTM, and then you can fuse it along with the acoustic score. This is the acoustic model score, and you can fuse it with the language model score using some weightage value, right? And that the hypothesis which you are going to generate is going to be better if you use if compared to the one which only the acoustic model is going to generate. So this is a very well known thing, and people use it a lot actually in speech recognition. It's like sort of like must to use language model for creating a better hypothesis, because the various reasons. And so that is the idea of using external LM. You can use it with different ways. I mean you can use a shallow fusion method, or you can use cold fusion method, or you can also use the deep fusion method, but here they are using shallow fusion method. So how do you generate synthetic data? So synthetic data is for example, let's say you have huge amount of text corpora, like thousands of sentences. So you take each sentence. So sentence could be like I am going to school, something like that. I am going to school, and you feed it to the parallel wavenet. It may not be parallel wavenet. You can use any other good state of the art text to speech engine. So when you feed this sentence to the parallel wavenet model, it gives you the audio signal, right? So you can use that audio signal to train the speech recognition model later, right? We'll see how they combine it, right? So this is how you can generate. I mean, parallel wavenet, as you can go and read about how parallel wavenet works. Like I will just give you an overview. Like it has a student and teacher network, sort of like knowledge distillation. They apply knowledge distillation here with autoregressive flow and different. I mean, it's a bit complicated. I mean, you can just go and read the parallel wavenet paper. So the idea is, given text data, you should be able to generate the audio. Right? That's the whole idea, and you can do it with all the sentences in your data and create a corresponding audio signal, right? Now coming to spelling correction model. So basically what happens is, you have the source embedding. You think of these are sort of outputs from the LAS model, right? These are vectors from LAS model. These could be let's assume these are characters, right? A, B, C, D, like, or it could be like hello world, right? So for every character you get a embedding, right? So in reality, these embeddings are for subwords, but let's just assume we have a sequence of embeddings for these characters. These are going to be the outputs from the LAS model. So these outputs may have some spelling mistakes. For example, instead of in hello you may have only HELO, right, instead of LLO. So you feed that mistaken sentence into the spelling correction model. So what output you get here is the corrected output, which is hello world, right. So this is the output you are going to get. So this is basically sort of mapping from one domain to another. Not one domain, you have some mapping where you take the spelling wrong spelling sentences and you map them to correct sentences. And the mapping function could be any neural network. In this case, it's a sequence model where you have an LSTM, multi-layer LSTM, along with the multi-head attention, and that output goes to a decoder, which will basically generate the correct sentence from the wrong sentence, right? That is the whole idea. And as I mean, this is just a sequence model with multi-head attention. As you know, like in sequence model, you have an encoder. In this case, it's LSTM, and you have a decoder that is also an LSTM. So the encoder generates hidden vectors, and decoder uses LSTM, so uses attention to look back in the encoder hidden states to take the ones which are going to have which are most useful for predicting the next character, right? That's the whole idea of using sequence model with multi-head attention here. And multi-head attention is just different version of normal attention. So as I said, so I'm sorry, I think there is a mistake in the slides. So so in the spelling correction model, so basically what happens is we have LSTM, so we have a LAS model where you have the LAS model is basically sequence model. As I said, it takes the audio signal and uses attention, and then it predicts the character sequence or word piece. Basically, it generates the word segment, subwords basically. So when you are generating subwords, so you are sort of doing decoding, right, in the LSTM, and since you are doing decoding and since it's sort of like when you are doing decoding, it becomes like this. So let's say the probability of the character A, then probability of character B given A, and probability of character C given B and A. So sort of like that. So you get it like this. So and when you are searching for the correct hypothesis, you will end up with multiple hypotheses. Since you are using beam search, you can have n different hypotheses, and you can rank them in probability wise. For example, the first hypothesis will have high probability, second will have lower probability, like that, right? So that way you get n different hypotheses for a given audio, right? They call them as H1, H2, Hn, and you can get the probability scores of each one of them. So these will be, let's say, these are in ascending or descending order, right? And what happens is the SC model. The SC model is basically these are the ones which are going to go as input to the SC model, and the SC model output should be the correct output. Correct output in the sense, if I have n different hypotheses here, let's say I spoke I am going to school, and the model predict I going to school. So these are the different hypotheses for the audio I am going to school, and I have the ground truth, which is I am going to school, and then we will use a SC model to map these H1s into the correct Weiss, right? And the SC model output is also in a sequence, since it's a sequence model, and there also we are using beam search. You can get n different hypotheses. Let's call them as m different hypotheses, A1, A2, AM for a ith sentence, right? So then and those probabilities you can call them as Q1, Q2, Qm. Now, if you are rescoring these when you start rescoring all these hypotheses, you will essentially get n into m hypothesis, and each one with its own score. When you rescore all the n and n into m candidates, you get n into m LM scores, right? As you can see here, R, right? And how do you get the final hypothesis? You can simply go and search the argmax. Basically, you do the search of this final equation where you take probabilities from these are the probabilities or hypothesis probability from LAS model. These are the hypothesis probability from the SC model. Then these are hypothesis scores from the LM final LM scores, and then you can fuse all of them together, and then you can get the final hypothesis which is going to have a highest probability, right? That's the whole idea of this paper. Actually, this is what they have done. And coming to the experiments, they have used Libri speech data, which is about 960 hours of audio data, and that is for training. And they have 5.4 hours of test data. And features, they have used 80 dimensional log mill filter energies computed for every 25 millisecond audio with shift of 10 millisecond, and also they are computing the velocity and acceleration coefficients. And for text only training, they have used around 800 million words Libri speech language model. And as you can see here, the out of 40 million text sentences are used to train the language model, and the same sentences were used to generate the TTS for training LAS model, right? And LAS model basically consists of two convolution layer and two convolution and three LSTM layers. As you can see in the encoder, and decoder is a single unidirectional by LSTM decoder, and they have used multi-headed additive attention instead of multiply or scaled attention, dot product attention, and they have used 4 heads, so the number of heads are 4. And they have used, as I said, they have used word piece model, and 16 word pieces have been used, the byte pair coding and encoding. And each word piece is represented by 96 dimensional embeddings, which are going to go as input to the SE model, right? And during inference, as you know, like they use beam search with beam size of 8 here. I mean, the beam size says they are using 8, and the training was done with synchronous stochastic gradient descent, because they were trained with different number of workers. Basically, they have used around 16 workers. And in the SC, basically the language model they have trained was a two unidirectional LSTM, 2-layer unidirectional LSTM, and again 16 k word piece tokens are used for the using training, and early stopping is used. And for synthesis, audio synthesis, they have used the parallel wavenet model, as you can see here. And since it's a parallel wavenet, it's a very fast, and it's high, the audio is high quality. And for the training of that model, they have used around 65 hours of female voice. And during training of LAS, they have combined both real audio and text to speech audio. And as they show here, during training they use 70% of real speech and 30% of synthetic speech in each batch while they are doing forward pass, right? And coming to SC model, SC has 3 bidirectional LSTM in the encoder, and 3 bidirectional unidirectional LSTM in the decoder, as you can see here. And residual connections are used, and same word piece, 16,000 word pieces are used, and searching is again done with 8 beam size 8. Regularization dropout rate have been applied, and attention is also used, as you can see here. Label smoothing technique is used, and then L2 regularization is used. So coming to the results, so as you can see in the results, first one is trained without any SC or any language model. You get around 5.80. You can ask a question like, how are you getting so much good accuracy without using a language model? Because since it's a sequence model, the LAS inherently has this property of a language model, because since sequence model, in the output when you are predicting, you will say what is the probability of A, then you will multiply what is the probability of given A, probability of C given B comma A. So this is sort of language model by itself. So you don't need another language model. But if you use the language model separately, you will get another one, some more improvement a little bit, and on the dev and on the clean. And if you use TTS along with the clean voice, so you get little bit improvement over this one, first row. It's just very minimal. And if you use LM to that, also you get very minimal improvement. And if you use SC spelling correction, you get it's a good improvement, which is about like 0.8% absolute improvement. And if you use SC plus LM, you get again a very good improvement. And here there is one thing which they observed was, if you use LAS with SC on the TTS data, if they measure the accuracy is very low in the sense the accuracy is very good. The word errors are very low, because the audio quality is very good. Since the synthesis is completely clean audio, the audio quality is very good. So what they did is, they just wanted to make it like realistic, so they added some noise to that TTS data, and that is called multi-style training. So that's MTR. So the MTR brings back the accuracy. I mean, the accuracy improves from 5.04 to 4.87, both with LM and with LM they get much more improvement, and without LM they get 4.87, which is very good. And that's it for this tutorial. Thank you so much for watching my video. If you have not subscribed to my channel, please subscribe. Thank you.